Okay, good, good morning. Let's get started. I think I posted some notes also for today's class. There's too much to cover in one class. So I'm going to give you very broad overview of these topics, and the actual papers and the notes that I have posted should help you to dig a little bit deeper into it. Okay. So we talked about this order book. Order book is place where buyers and sellers post their orders, and as I mentioned, some post them as visible orders, some post them as hidden orders. And in the last set of calculations, I noticed that in some cases as much as 40 to 50% of the orders could be hidden. Okay, and it depends on the, I get various estimates based on my own analysis of few leading stocks like Cisco and I think American Airlines and so on. We notice that roughly 20-25% of the stocks or orders are hidden. Okay, so generally I think we mentioned that we went through these order book cases here, and so limit order book is viewed as a queuing system. What they mean by that is that we have orders coming on the buy side and the orders coming from the sell side. There are also market orders that come, market orders that get cleared right away. Okay, they get the best price or best price and they get cleared. Okay, so I think the question is that in order to model this order book changes, so they look at this as a queuing system. You have queues on both sides, and then it's like supply queue and demand queue, and then the queues get cleared through market orders. Okay, these market orders could be new orders that come to the market, or it could also be that some of the limit orders get converted to market orders. Okay, so that roughly is the idea behind this paper by Kant and others, and I'm going to briefly go through them because it's a simple concept here. Essentially what this is just a notation to proceed here, and you have the best ask price and best bid price, and they usually put it as positive ask price, negative, just to see the distinction between the two. And so this is the probably the important slide. So market buy orders arrive at independent exponential times with rate mu, and limit buy orders arrive at a certain rate with lambda I. So similarly, you can also have sell orders arrive at a distance from I ticks from the opposite of the best quote. And essentially what they are saying is that if the best bid is here, the arrival rate of the ask prices are going to be, the best bid is here, the arrival rate of ask prices are going to be coming at a distance away from this best bid at a certain rate. Okay, so the idea being that usually you would see that orders that want to be implemented immediately, they all tend to come very close to the best ask, otherwise they are going to move away from the best ask. Okay, and then I think the cancellations of a limit orders take place. The cancellation rate is given as theta I x, and x here is generally taken to be the total number of orders or outstanding orders at that level x. The cancellation rate is given by theta I x. I think the key part of this paper is that all these three events are taken to be mutually independent. Okay, but we know that in practice, when actually they model this, there is some dependency, and once you start introducing the dependency, the derivation of any of these model results become pretty hard. So that's one of the reasons why they assume that, and they show that overall I think it works out better. It sort of captures the main essential points of the order book changes. Okay, so essentially this slide here talks about how the rate of arrival is going to change, and essentially when you say that P of AT minus I, you are looking at the best price minus how many positions you are away, As I mentioned before, I think many of these positions are just one tick away, just 1 cent difference or 2 cents difference. Okay, most of the changes you see in the order book are, somebody was mentioning, it's within a dime. It's not going to change beyond that. Okay, and so I think the order book is going to change whenever there is a cancellation, whenever there is an addition, whenever there is a market order comes in that clears the book. So there is all kinds of reasons why the order book changes, and this is the rate at which it's going to change. Okay, so you start with a certain configuration of the order book, and you can show that probability of a market buy order coming is given by these quantities here. Mu of A means average ask, and mu of B means average bid. So if you look at this, mainly the quantities are, you can see this is the arrival rate, is the mu of A, sort of standardized by all the other quantities here that's given here. Okay, and so if you look at this, you can see this is the arrival rate of ask, is just the sum of these two, arrival rate of bid and ask, plus this quantity here. This roughly captures the total market size at any point in time, because lambda bj is supposed to give you the the rate of arrival of bid orders j positions away from the best ask, and this sort of gives you theta j's are supposed to be cancellation rate, how many are cancelled. So essentially this kind of tells you the net orders that stay in the book. Similarly, I think probability of a limit buy order d ticks away from that can be also modeled as like this. Okay, so these results come out in a easy form mainly because of the assumptions that we have. The orders are all independent. Otherwise, it's very difficult to do this. Okay, and similarly, probability of a cancel order, again you can see that the numerator is the most important part. The denominator is the sort of same. Denominator sort of tells you the arrival rate of bid and ask here, and the second part of it gives you the cancellation and cancellation rates. Okay, so so the probability that a cancel buy order d ticks away from the best ask is given by that quantity there. Essentially, it looks at the rate of cancellation times what is the quantity left in the order book. Okay, so those are the main results here. Okay, and you can also see how do you estimate these things from the data, and you can look at the average size of the market order and average size of the limit orders. Generally, I think with algorithmic trading, you would see that the average sizes tend to be fairly low, fairly small. What they call one lots. One lot is 100 units. That's how they sell it. So the main thing that I want you to note here is that these two quantities are roughly the same. If that is the case, average arrival rate is going to be the number of average market order rate is going to be number of orders that come during that period divided by the total number of seconds in total trading days. So these are all pretty much based on common sense kind of estimates. Just look at the average arrival rate and so on. Okay. Similarly, the limit order rate function is given here. All these things are estimated based upon compiling all the data that you have at various positions and look at how many are at different positions. I think they sort of make this extrapolation because they can get fairly a good estimate for the first 5 positions. Beyond the 5 positions, 5th position, the rates are pretty uneven. So for that reason, they kind of assume that this sort of power law function, and they try to estimate this. They claim that that estimate seems to be fairly good in practice. Okay, so this has not come out well. If you look at the original paper, you will see that one bar is supposed to be the actual data, and the bar adjacent to that is supposed to be based on simulation. In most places, they seem to match up fairly well, and up to 5th position. After 6th position doesn't matter because we are approximating using the power law function. It's made to fix that way, so it doesn't matter. First 5 positions seems to work very well in practice. Okay. Okay. So there is this cancel rate function and so on. So I'm going to skip some of these things and then just want to get to this slide here. Okay. How do you use this information in practice? I think you have to see how the order book changes. So these probabilities are important. What is the probability that the mid price goes up before it goes down? And what is spread is equal to 1, and spread is greater than 1, and so on. So the question I think is that when you look at the order book, what can you say about the changes in the prices? After all, what is important is the mid price. Sort of that's the one that tells you how the price is moving. How do you look at this? So here is the table they calculate, and you can see that A is supposed to be the ask side and B is supposed to be the bid side. 1, 2, 3, 4, 5 means that 1 is the best bid and then 2 is the next best bid and so on. So those are the probabilities that we see, and this is just a empirical frequencies. I think you can, and then this is the second part of it. The bottom is the transformation, the estimated probabilities coming from the model. You can see they sort of match up roughly. Okay, it's not quite close, and this sort of validates the model that they have. Okay. Okay. And they also have this probability of executing a limit order. Remember, I think one of the decision trader has to make is that whether you want to send the order as a market order or a limit order. Okay. Market order gives them the immediacy, they get the price. You're like, what is the best price in the market? Limit order, by waiting, they may get a better price. It's also possible the market can move against them because this future is not going to be easy to be predictable. So I think they have to balance between the two. So this sort of tells you the probability that my order is executed before the ask moves are given by these quantities here. Okay, and these are all based on not the simulated data. Okay, so this is the probability of making the spread, and so on. So the paper to read is going to be this Kant, Stykov, and Trulreja paper. I think that's the only paper I've seen that is more rigorous in modeling order book dynamics. And this topic, for some reason, did not get much attention because you will see that now we have to study not just one order book, we have to study multiple order books. Okay, so how do you estimate these model parameters with level 2 trades and quotes data? Remember, level 2 is supposed to give you a little bit more information, and I don't think there is any study that has proceeded after this. With level 3 data which we are looking at, we can trace each order and see whether that order is converted into market order, whether that order is cancelled, and that sort of information is very easy to get. So we can study the cancellation rate better. Okay. So with multiple exchanges, what's happening is that traders are submitting same size orders to various places. As I mentioned before, what we are finding in our study is that once the one order gets executed, the other orders get cancelled in milliseconds very quickly. Okay, so there is this idea here. So I think there are a few things that one has to work on. I think the time between two orders is taken to be exponential, and based on the duration analysis that we have seen in the class, we know that there is some dependence between time arrivals. So I think that information is never taken into account. Okay. So formally, to model this in a setting like order book setting when it changes so fast seems to be rather difficult. Okay. I think the next set of things go into optimal execution. Okay. So when we talk about optimal execution, okay, there are two types of cost. I think I have an estimate in my next set of transparencies I'll show you. One is the direct cost. Direct costs like commissions, taxes, and other things. So those are generally fixed a priori. So you know before even trading how much those costs are going to be, and they are easy to measure. Okay. There are indirect costs. I think these market impact. Sometimes I think the mainstream finance calls it as price impact. And opportunity cost is that if you don't trade it at the right time, how much money you are likely to lose, right? That's opportunity cost. And I think the price impact, the way they define is that what would be the price that would exist if you have not entered the market, okay? Which is very difficult to, conceptually very difficult to test out. You have to enter the market to see how it's likely to change. So usually what they do is that they look at, after they enter the market, how the price changes over time, okay? And you will see that that is a major component of cost, And the next set of presentation, I'll show you how to measure this, okay? So trading has changed because of the order book here, and okay. So as I mentioned, what is the best method of trading? So there is a trade-off between one large trade that will affect the stock price adversely, or splitting into equal pieces, let market recover after each trade. I put equal pieces, doesn't have to be equal piece, splitting into pieces so that the market recover after each trade, okay? So there are two types of cost people measure. One is called permanent impact. Permanent impact is that after the trade is over, what is the price that comes up? That is a permanent impact. That is the starting price and the difference between starting price and the ending price. When I say ending price, 30 minutes after the ending price, okay? And there is also temporary impact. Temporary impact is that as soon as you make a trade, the prices tend to oscillate and then it settles down. And again, another trade comes, again it oscillates and settles down. So that is called temporary impact, okay? I think all the models I've seen to measure temporary impacts are mostly conceptual models, and estimating this are not easy because, as I mentioned, the order book changes every millisecond. It's very difficult to see the impact, market impact of an order, the temporary impact of an order, how long it's going to last, okay? So there is a, okay. Let me go back here, okay? So the cost, I think, loss in revenue due to the price impact, uncertainty due to volatility in the underlying stock, that is a risk. If we trade very fast, we incur high cost and low risk. If we trade very slow, we incur low cost and high risk. How do we achieve the trade-off, okay? And there are a couple of procedures that we'll see. I think if anyone wants to work in this area, I think these are the major papers to read. The first paper, I think Kyle 1984 paper, they say that it's one of the most highly cited paper in finance. Essentially what it says is that the basic premise of that is that if somebody wants to hide private information, they are going to split the orders. They are not going to keep the parent orders the same size because they want to send the orders in smaller sizes so that they don't reveal their hand. That's the main idea of Kyle's paper, okay? And the sequence of papers that led to electronic trading actually started with Bestimos and Lowe. They want to split the parent order to reduce the trading cost. And the Omgren and Chris celebrated paper is split the parent order to minimize mean variance of trading cost. And the paper by Engel and Festenberg split it to maximize Sharpe ratio. I think the question, I think, is that how do you achieve a trade-off? Trade-off means that putting all the orders at once versus splitting the order over time. How do you get the trade-off? Okay? So this is the paper that I want to mention here. Okay? So let me briefly write the basic idea so that you can see. Yeah. So I won't go too much into depth here, but I want to briefly mention here. So we have X is the total number of units that you want to sell. That is the parent order size. So you want to divide this into n child orders. And I want to write this mainly because in duration 0 to capital T, so this is the parent order. And the question is that how do you divide this into n1, n2, etc. up to nn. These are the sizes of the child orders. Okay. So based on my research in this area, you will see that the number of child orders could be as large as 300 orders. Okay. So if you have a large parent size to be traded, so it becomes, they divide it into very small quantities and send it out. Okay. So I think I mentioned this, if the P0 is the initial price, sometimes we call it as arrival price. And the quantities that we look at is the average executed price. This is defined as n of j, whatever the price that exists at this point here, j ranging from 1 to n. And they also look at volume weighted average price. Volume weighted average price is whatever volume that gets traded in the market, because there are players besides you, so you look at what is the volume that is bought over that particular day, Pj star, divided by the total volume. Okay. So as I mentioned before, the way they measure how good the execution is that by comparing this quantity with this quantity here. Okay, that is a price you would have gotten if the liquidity was available at that price when you entered the market, right? So they also look at the difference between these two. So this is the market execution price and this is your execution price. If that is the case, what is the difference between the two? So those are quantities that people look at in practice. Okay. So we'll come back and comment a little bit more on this later. Okay. So the strategy, I think one of the strategies that was mentioned in Max's lecture was that what they call TWAP. TWAP is time weighted average price. Essentially, you decide to divide this up into certain number of units and parcel it out on a periodic basis. That's what it is. Okay, but the one that is used in practice is that what they call is that BBOP strategy, BBOP allocation strategy. So this is essentially looking at n of j over x is equal to v of j over v. So essentially this implies that the number of units you want to sell out at any duration of time, this usually is say every 5 minutes or whatever, you can get this. That's a method that you use. Okay. And in order to do that, in order to implement this, what are the things you need to know? So in order to implement this, you have to know what is the volume going to be next day. You also have to know what is the volume going to be the duration that you are trying to send out the market. Okay? And based on the volume modeling, you already know that the volume is not going to be constant throughout the day. It's going to change within a day. So you need to have a good forecasting for these two quantities in order to estimate this. Okay? So there's a lot of time spent by these guys to estimate this carefully. Okay? So that is the PBOP strategy. The second set of procedure, I think, is starting with Best-Mass and low. Start the following. So let me define here. Okay. This is Best-Mass and low paper. So this paper actually led to a lot of research in practice. So what do they say? So they define x is equal to, so x times P0, that is the value that you would get if you could sell whatever you want at the time of entry, x times P0 minus the average value you end up by parceling this out over n periods. So this is nothing but you can see that this is same as writing x times P of 0 minus x. Okay. So this quantity that I have written here is known as implementation shortfall. Implementation shortfall. Okay. So what is the model they what is the program that what is that they want to do with this? So your goal is to minimize the implementation shortfall. You want to select the values of n. Values of n are nothing but the sizes of the child orders that you want to parcel out. Okay. So essentially their problem is that minimize nj and expected value of x. That is the average implementation shortfall or average cost, minimum of n of j. Essentially this is nothing but expected value of x, p of 0 minus sum of 1 to n, n of j, p of j. So that is the model they use for doing this. Okay. So if you look at these quantities here, which quantities are known to you, which quantities are not known to you? You know how much you want to, what is the parent size, right? X, capital X, you know, and you know what is P0 when you come in. So those two quantities are known to you. But if you look at this here, we don't know what the future price is going to be, right, as you enter the, and this is the quantity that you need to decide. Okay. So in order to make the model work, they assume that the prices follow. What is the usual assumption we make for price? Prices are supposed to follow random walk model, right? So we have this P of j minus 1. But they make one other assumption. This is like theta times nj plus epsilon j. Okay. So where theta is positive. Okay. So what is the role of the second term here? It sort of gives you the impact of your selling, right, on the price function. Okay. Sometimes this is known as impact function. Impact function. So essentially I think this problem here can be written as follows. Take that problem there and then write it as follows. Okay. So, so since the first part of this is sort of known to you, just have to worry about the last part there. So that is that you can show that minimize or maximize, doesn't matter here, minimize n of j. The key part of this is that you want to be able to say what those n quantities are going to be sitting at period 1, okay, j ranging from 1 to n of j, p of j, such that the total n of j is equal to x, 1 to n. So, okay. So this is the optimal control problem, right? Sitting at period 1, you want to know what the sequence of n is going to be into the future. Okay. So the way they solve this is that, using Bellman equations, essentially you solve from the end to the first value. Okay. So I'm not going to write this in a way. I think I'm going to write only one line and then I'll give you the solution. Here you can refer to the original paper here. Sequence at any point here, nj star, nj plus 1 star, etc. up to n of n star is optimal must be optimal for at any stage E of j, k ranging from j to n, n of k, p of k. Okay. So essentially the problem works out as follows. The details are given in the paper. It's very, very elegant paper to read. You'll see that you start from the last step and work your way backwards. So you can show that the resulting Bellman equation can be written as follows. So let me write this and then I'll give you the final solution here. Okay. So Bellman equation. Okay. So this is given as the value at any point in time is n of j is given as minimize n of j. So you look at the expected value of this at step j is n of j p of j plus, and the value at j plus 1 p of j n of j plus 1. So you solve this problem sequentially. So you can solve from the end and sequentially backwards. You can show that the resulting strategy is going to be that n1 star, n2 star, etc. up to nn star is x over n. So essentially Bellman equation, essentially Bessemer's and Low paper says that take this parent size and divide it equally. That's all it says. Okay. So that's the very first paper here. Okay. Does anyone know why we are getting such a simplistic answer? What is the reason behind getting such a simplistic answer? Anyone? Actually, it goes back to this model that we have here, right? We are saying that the impact function does not depend upon prevailing price, PFG minus 1. It is just independent, just depends on the size. So it does not depend on the price. So I think that's the reason why you get such a simple answer. Okay. So this was the original work, and I think some of the traders were using this kind of model before. This kind of justified it, but the moment you start making additional assumptions on the impact function, the calculations become pretty complex. Okay, I think there are a couple of ideas that. I have one more function here. There is a short write-up in my book on some of these things. If you get a chance, take a look at it. I think if you modify this particular equation to depend on P of j minus 1, you can show that the problem is not that simple to solve. It's much more complicated. Okay. So this was the paper by Berstimas and Lowe. Then came the Almgren paper. Okay. I don't want to get lost in the notation here, so I'm going to write a simple way to trying to see. There is one other model that I wanted to mention. So if you look at Berstimas and Lowe paper, so they sort of extend this to one other function. That's what I was looking for. Okay. So what they say is that if you could say that P of j is P of j minus 1 plus theta times n of j, and they add this additional term here, gamma of y of j. I'll explain what y of j means, epsilon j. Okay. So y of j is supposed to be rho of y of j minus 1 plus eta j. Okay. This is eta j, sorry. Eta j. So this is supposed to be the state variable that reflects the market condition, state variable. So they sort of bring in the memory part of it, taking the previous, the influence of the previous value on the current value using this equation here. Then they show that, you know, the whole thing becomes a little bit more complicated. Okay. In fact, they have some good clear solution for how to solve this problem. Okay. And in practice, we know that, especially in the context of order book modeling, we have seen that in the high frequency setting, there is always some memory, right? Remember, we talked about moving average model. So one could introduce that and see how these things will change over time. Okay. So let me write down what the main idea behind Almgren and Chris paper is, and then I'll give you the summary results. And I don't think we have too much time to go through the calculations, but let me. So the second set of papers, I think, is given by Almgren and Chris. So their main idea is to minimize, okay, essentially minimize n of j, Okay. So, they want to look at expected value of x. X is the same as what we have defined before. It is the implementation shortfall plus lambda times variance of x. Variance of x. Okay. So, it is the same as the problem before. I think in the case of Bersimas and Low, they did not have this term. Here they look at this. What is the usefulness of putting this variance of x term? What is the usefulness of that? Variance of x is supposed to be variance in the implementation shortfall, the cost. As we mentioned before, if a stock has a higher volatility, right, weighting is going to increase the variance, so that has to be accounted for. So that's the main idea here. Okay. So the solution and all, you can go through this. It's fairly elegant solution they have given. If you go through the concepts here, I think all these things are just leading up to solving that problem there. So when you do this, this is what we get. But before I get to it, you can see price is supposed to be a random walk, and you can see that here P of k is supposed to be P of k minus 1, and this is nothing but variance term. They also introduce like gamma times nk, which is nothing but like theta times nj that we had there. It's a market, it's the impact of your trade size. That's what they introduce. And under that model, I think there is no drift, no information about the future price. You can show that the solution turns out to be, I think I'm just going to quit here and go to the final solution. So the final solution is given by those quantities there, x of j and n of j. Okay. And it's very easy to go through this. I think if you substitute values, you will see. And if there is a short drift in the parameter here, and the short drift is taken, this is a short drift here, and you can see that solution is pretty much a similar solution you can get. Okay. In fact, I think they show that even if there is a serial correlation in the error term here, remember that correlation is possible if you are dealing with high frequency data. Even that is accounted for. Still the form of this is going to be pretty much the same. Okay. So I think it's a very, very nice solution they've given. But I want you to look at the following before I do that. I'm trying to see where is the, this is all here. So I want you to notice that there is this quantity, the concept of temporary impact they measure here, and you can see that the price is supposed to be influenced by this temporary impact. The idea, I think, is that as soon as there is a trade, it's likely to bounce the price, and how much it gets bounced is measured by that quantity eta. N of k is your trade size, tau is supposed to be the duration in which you are trading, so that is the impact of that. Here, I think the idea, is that they are looking at it from selling side. So if you sell more, you're supposed to influence the price to the lower value. So that's how you get that equation. Okay. The reason I want to point that out is to show you that the quantity that plays a role is, they call it as urgency parameter k, which is lambda is how much importance you want to give it to the variance term, and sigma squared is the volatility term, and eta is the quantity that was mentioned there. That's what they call it as urgency parameter. I want you to keep these things in mind, because when we do the actual market impact modeling, you will see that sigma squared, the variance, plays a very important role. Okay? I'll show you the empirical study that we have done in this area. Okay? So this was the graph I think that Max also mentioned here. So idea being that you can see that lambda is the complexity parameter here. So a lambda is equal to 0 means that roughly the variance is pretty much constant. Sigma squared is almost, price is constant, sigma squared is almost 0. If that is the case, you'll use the linear function, which means that you can trade evenly over time. And as lambda gets more and more important, which means the variance is higher, usually you want to trade faster at the beginning of the trading period and then slow it down after that. Okay? So there are some various models they fit and they seem to work well in practice. So this sort of gave the the first, I think, the electronic trading algorithm, that is that how do you divide the parent order into smaller size. Okay. So there is a still I think this sort of mention how do you execute a large block and mean variance objective. The main issue with this Armgren and Chris paper was that the trading schedule is fixed ahead, right, over time, and that is how do you change that? There's a paper by Lawrence and Armgren. Lawrence was supposed to be his Armgren student. Essentially, he looked at Bayesian updating. So at any point in time, you look at what the market is, and then you change this sizes accordingly. So there are a few thoughts like that. Okay, and I think how do you do this for multiple assets? So there is a section in Armgren and Chris paper. If you want to do it at a portfolio level, which means that you need to liquidate multiple assets, and how do you parcel that out? Okay, this is something worth reading. Okay, before I get to smart order routing, I want to mention that there are few other papers worth looking into. I'm going to give you only a couple of them here, and I think the other paper that came out after this is Engel and Westenberg. So their goal was to same function minimize n of j. So instead of looking at this, they look at expected value of x, variance of x. Okay. So they want to minimize that quantity here. So does this criterion remind you of something? It's like the Sharpe ratio. That's what they do. Okay? So I don't think there is any explicit solution they mentioned, but I think one should be able to obtain that. Okay? So and then came actually this paper has been around for quite some time, but it got recently published here, Obizawa and Wong. So what they did was to account for the dynamics of the order book. Okay. So I'm just going to write the basic ideas here. Model incorporates bid-ask spread, and also looks at market depth. I think the other model that I'm going to mention also takes into account market depth. And so here I think these two quantities are sort of estimated from past data. They call it as static aspects, called static aspects of liquidity. So they also look at the dynamics of that, they call it as resiliency dynamic aspect. Okay. So essentially how the future limit order book evolves depending upon the current state of the order book. Okay. So optimal strategy depends upon the combination of generally what you consider as the static aspect and this dynamic aspect. It's a combination of the two. So their suggestion is that combine large and small orders. Okay. So essentially be flexible. Don't fix your order size to be a priori, but you change it depending upon how the market changes. Okay. So I think if you look at these papers before, they have certain regularity. They all seem to depend upon fixed variance of the stock, and then they go through that. Okay. And the other paper that I want to mention is by Easley and O'Hara and others. Okay. So this one actually is very interesting. They talk about optimal execution of horizon. Okay. What exactly they study? Okay. So if you look at the basic setup, we are going to assume that there is parent order capital X, and we are going to trade it during the duration 0 to capital T, right? So usually in practice, it's traded in one day. They start in the morning, they close all the position by end of the day. Okay. Here I think they focus on that capital T. Can you make it shorter? Does it depend upon the size of the order that you have, the nature of the market, and that sort of thing. So here I think the focus seems to be, in addition to all the other factors that we have seen, how do you decide on capital T? What should be the capital T? Okay. So this is sort of the evolution of these papers here, but there is still one unsolved problem here. That is that how do you decide how many child orders you need to send out? Okay. How do you decide on N? Okay. What should be the value of N? Okay. So that is still a sort of an open problem that one should look into. Okay. Okay. I think we are running out of time, so I'm just going to briefly mention what is the idea behind this smart order routing. Okay. Remember, we talked about multiple exchanges, so you need to decide. It's a two-step process. One is that you need to decide whether your order is going to be limit order or market order. Then if you decide to be limit order, you have to decide which exchange you want to send it to and which position you want to place your order. Okay, those are questions that we need to look at. And as mentioned before, I think there are several, the size of the hidden orders depending upon which study you look at could be anywhere from 12 to 45% of the orders. Okay. So this is what we have, multiple limit order books. Each exchange has its own order book. But luckily this rule, I think this best bid and best ask, that's what you're supposed to get when you send the market order, puts a binding on all the exchanges to honor the best order that's available. Okay. So there are some studies that are done here, and I don't want to spend too much time here. Let me give you the key points here. The key points is that same as the study we saw in Ramakant's paper, where you look at limit orders come at a certain rate, and market orders come at a certain rate, and you combine the distributions and come up with the probabilities of getting executed. This is roughly the idea here. The limit orders have a certain rate, lambda 1 to lambda n, and market orders come at a certain rate, and then the market orders come at a certain flow from the other side. Okay, so this is the main question that people ask, is that how do you estimate this lambda? Do the limit order flow to different exchanges vary at different points in time, and do the market orders vary? And this is where I think the fee structure come into play. Remember, we mentioned that different exchanges have a different fee structure. If you post an order, some exchanges give you some rebate. If you take liquidity, some exchanges give rebates. So these, I think some of these things were posted actually in, if you look at Peter Layton's presentation, there is a long list of fees and rebate structure that was posted. Okay. So if you go through this, I'm not going to spend too much time here because I want to get to the other study that I mentioned here. So if you go through this, I think what is the main idea here? Okay. So first of all, I think you need to know where the orders go. Okay. For instance, if you look at tech stocks, Microsoft and Oracle, the main exchange they trade is NASDAQ, and the trading occurs in other places too. If that is the case, which exchange they send their orders to mostly? And you can see that this is supposed to be the rebate and fee structure. This is a little bit old actually. The structure has changed quite a bit recently. And then this is the market order routing decisions people make. So essentially the largest place where they send is taken to be 1. And this, you can see, ARCA, BATS, and EDGAR gets more orders than NASDAQ. Okay. So I looked at this data for 100 stocks. The main idea seems to be that whenever there is a excessive, you have a volume expectation, certain volume is expected for a day, but whenever there is additional volume that comes in, I wanted to see where this additional volume flows. And generally, they tend to flow almost in proportion to what the volume distribution was before the excessive volume came. So if NASDAQ is the major, that's where it seems to go. Okay, and I need to look into this data a little bit better. I don't have access to it. So here is the adverse selection estimation quantities, and you can. I think the question I think is that by sending it to these exchanges, or the prices improving or not improving. In fact, our study shows that I think if you send it to the exchange where the most trading occurs, you still get good price. Okay. So I would like you to take a look at it. I don't want to go too much into detail here. I want to get back to my market impact model study that we did. Sorry for posting some of these things in a last minute because I think for most part I'm going to go through a study that we did for JP Morgan Chase, and a study that we are trying to get published. Okay. So let me what is the price impact difference between the price and the price if the trade has not occurred? So generally I think you would see that buy trade should push the price up, sell trade should push the price down. Second buy trade is on the average is more expensive than the first one. Okay. So usually market impact is measured by correlation between incoming order and the subsequent price change. Essentially how the current market order influences the price of the future. Okay. So this is an interesting area of research. Okay. So we talked about these execution layers, and I don't want to go through this. So this is a table that I would like you to take a look at. Okay. So this is the cost estimate table that was put out in 2010. So all the numbers that you see are supposed to be in basis points, and if you look at the numbers there, which variable has the highest cost? Can you see that market impact cost the highest, 35 point? All the other things are fairly, compared to it, it's not that high. Okay. Bid-ask spread, which we talked about before, is a cost of trading in a way. If you want to cross the spread, is 1.9 BIP, and then the delay cost is 9.5, and so on. You can see that market impact cost seems to be the major cost that one has to worry about. Okay. So these are the benchmark price examples that we went through before. So essentially, people look at the VWAP price versus arrival price to see how good they are. So the strategies that were mentioned before is that you want to minimize the difference between VWAP and executed price. This is the implementation shortfall strategy, and this is the percentage of volume strategy. Percentage of volume strategy is fairly simple. You don't worry about the price part of it, just parcel out the way the volume gets distributed over time. Okay. And there is also slippage that people talk about. Slippage is mostly between benchmark price and executed price. What is the benchmark price? Benchmark price could be the arrival price when you came. It also could be, what is the market price, VWAP price, and so many other things can go into the calculation. Okay. So this is how they use it. When the client comes with a large parent order, they need to give an estimate of how much it's going to cost them. As I mentioned, the cost estimates for known costs are fairly easy. Unknown cost is the price impact cost. So you need to come up with an estimate. Then usually it's sort of, after you do the trading, you evaluate what went wrong and then try to adjust it. That's the idea here. So why is there price impact? I think traders successfully forecast short-term price changes and trade accordingly. Okay. If the market is efficient, you should not see any of these things happening. And it also could be that they have trade in private information, they trade on that. There is also statistical effect mainly due to order flow fluctuations. Okay. So if you look at 5-minute data, I've looked at it, you'll see that the flow comes in certain periods, a constant basis, and then it slows down. So we don't know what the reason is, because it's possible that the prices are not moving, so they slow down the trading. Okay. So how to distinguish between market friction and new information. Okay. So I'm not going to go through this here, but except to point out that the famous Kyle model assumes that there are two groups of traders, informed traders and noise traders. And in those days, I think there was a market maker, the person who deals with both of them. And then, yes, he cannot distinguish between informed trader and noise traders. So he has to set a price, and he goes through these things. But the main point of this is that the impact function is supposed to be a linear function of the price. Okay, that's what okay. So there is a lot of work done here. So I would like you to take a look at it, because this is fairly a comprehensive review of market impact model. Okay, so let me. So this is the formula that's used in practice. They call it square root formula. And if you look at the softwares used by all these Solomon brothers and so on, starting from 1991, they pretty much use the same model here. Okay. Delta P is the price change after you enter the market. So it's supposed to be spread cost, which is the bid-ask spread. And then you have this sigma is the volatility of the stock, square root of Q over V. Q is the parent size order that you send out. V is the total volume that happens. Obviously, you can see that if you are going to be a major player, Q over V is going to be fairly large, then your cost is going to be higher. That's the idea. And it also depends upon the volatility of the and alpha is a constant, generally close to 1. Okay? Essentially, this equation is fairly simple. I think you can estimate how much it's going to cost very easily by looking at the past average spread, and then you know what the volatility is, and then you can decide based on how many units you want to sell, that's the cost. Okay? This actually model works pretty good in practice. So that is just rewriting this model in that form. So essentially looking at this is the deviation that you see from the spread, and then adjusted for the standard deviation of the prices, standard deviation of the returns. Okay? So the square root formula refers only to the size of the trade relative to the daily volume. Actually, it doesn't take into account the rate of trading, how the trade is executed. It doesn't talk about the capitalization of the stock. Okay? Because making the distinction whether you are dealing with large cap versus small cap seems to make a difference. Okay? So let me give you I think we are running out of time. Let me get you the study. Okay? So in this study, what we did was we wanted to look at what are the key determinants of market impact in the algo trading context. Most of the studies, starting with Kyle's work and so on, they were done on a slow trading. It's not based on the fast trading part. So we had access to this information, and we also had information on whether we are looking at buy side or sell side. And then is the cost different for ETFs? Okay? What is your guess? Do ETFs change faster than the individual stocks? You will see the cost for ETFs generally tend to be very low. Okay? ETFs tend to be small. Okay? So these are the key determinants. You'll see the trade size as positive impact. Market cap is plays a role. We also looked at volatility, trading activity, and time of the day. And then we wanted to see what is the impact here. I'll just get to the main part here. I think so. This is the basic data that we have. We have over 250,000 parent orders. Generally, the strategy they used was that VWAP strategy for a period of 1 year. And each parent order was sliced into several child orders, and it was executed in more than one fill. So these are the stock related variables, and you can see we looked at the daily volume, annual volatility, and so on. So but the average daily volume is taken to be average over the last 22 days. That's the average volume we used. And we also have this market beta of the CAPM model, and then this is the trade related variables, average trade size, side, the number of child orders, and so on. And trade duration, I think that's sort of redundant quantity here, because usually it's just 1 day period. Okay? And we computed all these variables here. I'm going to focus mainly on this transaction cost, average fill price minus arrival price divided by arrival price. Okay. So when we did these things, there was lots of unusual observations. We have to do some data cleaning, but after we did that, you can see sell side and buy side are split evenly. Okay. I think the value of this data we thought was having this information on sell side and buy side, because if you use the trade and quotes data that you get from birds, that information is not available. You have to guess it. Okay. Here we had a clear information. And these are the distributions that you see. You can see the transaction cost could be positive or negative, mainly because I think if the market is doing well in your favor, cost is going to be negative. The market is not doing well, cost is going to be positive. Generally, price impact is supposed to be looking at the positive side of the cost. Okay? And you can see that most of the stocks we had as a market beta of 1. So we had lots of stocks very close to that. Okay? I think we had over 4,500 stocks or something like that representing this data. Okay? So we had to do some data smoothing. We just did all these variables that we took and put them in bins. And if any combination of the bins has less than 20 parent orders, we took it out just for the sake of. So this is what I want you to see. Okay? You can see that this is the transaction cost, and that is the relative size. Relative size means that Q over V. Q is the parent order size divided by the volume. And you can see that it's fairly, it's a square root formula, holds very well in practice. And the second one is the duration. How long does it take to do this? I think here we took the actual duration for trading, and duration does have different durations have different impact. And I think I think this graph is probably the useful one. This is supposed to be the volatility graph. You can see the red graph is supposed to be with low volatility, and the blue graph on top is supposed to be with the high volatility. You can see that if stock has higher volatility, it has higher trading cost. Okay? Seeing all these things we have tested out through regression. Okay? You can see that is model 1. So if you look at model 1, relative size, the coefficient is 0.53. It's almost a square root model. It tends to work out well. And since we have smoothed the data, we get such a high R squared. Otherwise, we won't get that kind of high R squared. Still, I think there is a lot of variance to be explained here. You can see that the unexplained variance is total variance 111, unexplained variance is roughly 70 here. Model 2, we brought in volatility. You can see volatility is significant. Model 3, we brought in duration. I think duration is negative sign, as you would expect. Longer the duration, I think the cost is less. Model 4 sort of brings in market cap, and market cap is significant. And lastly, model 5 has number of children, which is also significant. Okay. So I will post the paper. I think I have a copy of the paper which I will post it. You can take a look at it. So the main ideas are the following. The main idea is that volatility does play a role, right? So this model can be used to give a benchmark estimate of how much it's going to cost to the client. That's how they are using it now. Okay? The key question, I think this paper, I think we submitted, got rejected in couple of places, mainly because why the number of children plays a role. So our argument is that the number of children is that how you divide this up and send it to the market. If the people can assess that this particular child order comes from the same source, then they can move against you. That's the idea here. Okay? So we're still not able to, the optimization problem that I mentioned here. So if someone can work on this kind of optimization, where you not only look at n of j, but you also want to optimize for this capital N. Okay, capital N is the number of child orders. If you can simultaneously optimize the two, what would be the result? We don't have yet. We are just beginning to work on that area. Okay, so I will post these things on the coursework. Take a look at it. If you offer any comments, I would appreciate it. In fact, I think if you look at later on, I'm showing here. So this is the transaction cost plot for ETF versus non-ETF. You can see this is supposed to be non-ETF, and the predicted value means it's a combination of all the variables that I mentioned before. and you can see that, you know, this is ETF costs go up, whereas, sorry, the non-ETF costs are going up, ETF costs are fairly flat. Okay? So this was probably one of the first studies that shows the difference between ETF and non-ETF costs. Okay? Any question? Any question? I think we have gone over time. Any question? Okay, I think today is the last class, you know, like everything else, it has to come to an end. So give me your feedback. I do take teaching very seriously, and your feedback is very important to me. And I think, you know, come to think about it, I think we have come a long way in teaching this course. When we started, I started in 5 years back, you know, I didn't have any material to work with. I think slowly, I think we have developed it. And I also want to take this opportunity to thank Leo, who has been very dedicated to the course, and Licky, who has been very good to the course too. Okay, I'll stay around for a few minutes if you have any questions. Okay, thank you.